My iPad is not working. In case I want to just write something, let me get something out. Yeah. So I know what Mustafizur and Janani, some of them have covered with you all. And I know that you all are more or less familiar with what is expectation value calculation, how that is done. So the first half of this talk may be, okay, sorry. The first half of this talk may be uh, a bit repetitive to you, but I am really hopeful that it won't be completely repetitive and you will get something out of this, something more than what you already know. So you all know what is expectation value calculation. Let's look a bit into why that is useful. So let's think of expectation values and why that is useful. When we think of quantum computing or quantum mechanics in general, we have a wave function there, which is usually denoted by this psi. And this wave function, the way Schrodinger says that if you know the wave function, you know everything about the system. But the point is that we usually like to measure certain things. Say, I want to measure the momentum of the system. I want to measure the angular momentum of the system. And so many things that I can want to measure. And there are definite things that I can measure about the system. There are things that I cannot measure about the system. So the things which can be measured about the system, these are called observables. Sometimes I like to joke that observables, what are observables? These are things that you can observe. In some sense, that's true. So all the things that you can measure, these are denoted by an observable. And mathematically speaking, these observables are Hermitian matrices. So what is an Hermitian matrix? It is a matrix where H, which is its own dagger. Dagger is the complex conjugate transpose. So a matrix which is its own dagger, that is the called a Hermitian matrix. Observables are Hermitian matrices mathematically. These matrices have a property, and the property is, so what happens when we measure something? We know from the measurement principle that when we measure, the system collapses. And if we know the observable, the outcomes can be the eigenvalues of the observable, the value of that exact state, or the exact thing that you are going to measure. Say I am going to measure momentum. What are the possible values of the momentum? They are the eigenvalues of this observable. And once you measure the system, we know that the system gets changed. How does the system change? How do I know that? When we get a particular eigenvalue, the system collapses in the corresponding eigenstate. So if we can say that H is my matrix, which has, say, a set of eigenvalues E, and the corresponding eigenstate is this ket E, which is a quantum state. And we can have, say, n many values, E1, E2, E3, up to En. So n many values are possible. When we measure this, the value that we will observe is one of these E's, say EI. And if we get the value EI for, say, momentum, if we get the value of momentum is EI, the system will go and collapse in the corresponding eigenstate, which is this state. Now, there is a very interesting property of Hermitian matrices, which becomes very useful here. So we always know that if I give you a general matrix, the eigenvalue itself can be imaginary. But at the same time, when we measure something in this world, nothing is imaginary. We get some real values. So the property of Hermitian matrix is that all its eigenvalues are real. So this guarantees that when we are going to measure something, the value that will get is a real value. It makes some physical sense. It's not something abstract that I am talking about at this moment. So now think of this, that when we have a quantum state psi, we know that a quantum system, sure, I hope this is better. So we know that a quantum system is probabilistic. So just as we said that it can collapse to any one of this E and there is an associated probability. So we can say that there is an associated probability. Whenever we have something probabilistic, it need not be quantum. Even classically, we do all these randomized algorithm, all of these things. So whenever we have something probabilistic, if we just go and measure it only once, that is never sufficient. Like we say that if we flip a coin, it is 50% chances 50-50 will get head or tails. But if we flip the coin only once, we will get either heads or tails. That is not giving us the entire picture. That is not giving us the entire statistics. So if we want to know the entire statistics, we need to measure it again and again. So the number of times we end up measuring it is called shots in Qiskit. This is Qiskit terms, but not a problem. Like it is called shots in Qiskit. How many times you are measuring the system? And when we measure the system, say I am measuring it 100 times. Of this, say 50 times I am getting eigenvalue E1. Then say 20 times I am getting eigenvalue E2. And say 20 times again I am getting eigenvalue E3. And 10 times I am getting eigenvalue E4. If I do it again and again. So now what we do immediately on even randomized algorithms or probabilistic thing, we calculate expectation value. So what is the expected value of outcome that we are going to get? So the expectation value will be, say 50 times I have got E1. So 50 by 100 into E1 plus 20 by 100 into E2 and so on, so on. So when we do this kind of thing, what is the quantum part and what is the classical part here? See, the quantum part is simple. Preparing the quantum state psi using some quantum circuit. This is the quantum part. And this is the quantum part. And then we measure the state. Well, measurement also in some sense is quantum. But once we do the measurement, say 100 times, we get this statistics out. We calculate the expectation value. This is totally classical. There is no quantum when we actually do this calculation. So quantum part simply is preparing the quantum state, measuring it again and again. We get the different outcomes. Once we get the different outcomes, we do this calculation classically. This is simple addition and multiplication. There is no quantum in this. But why is this expectation value so important? The reason is for many problems that we would like to solve using a quantum computer. Say I want to solve a quantum chemistry problem. Given a molecule, I want to know what is the ground state of that system, what is the ground state energy. So what we can do is we can carefully prepare an observable that will be a representative of that ground state. So when I measure again and again, my expectation value gives me the expected ground state energy, and my corresponding eigenstate gives me the ground state. Say I am doing a optimization problem, combinatorial optimization. I want to know some graph property. What is the size of the cut of this graph? What is the number of, what is the size of the vertex cover or something? I'll prepare my observable accordingly so that my observable will tell me the vertex cover size, or it will tell me the edge color, number of edge colors required. And when we get the expectation value, it gives me the solution to that. And the corresponding eigenstate is give me, say, if I'm doing the coloring, it is giving me the actual coloring of this. When I'm doing machine learning, I will prepare my observable in such a way that the result will perhaps give me the, say, F1 score, or what is the training accuracy or testing accuracy, something like that. And my corresponding expectation value, when I measure this observable, will give me the actual, say, training accuracy or something like that. How do we prepare this observable? This itself is a very difficult question. I mean, it is not a question to solve in one class. It will take many classes. And this is kind of the most important research question, that if I give you a quantum chemistry problem, say if I tell you that you need to find the ground state of lithium hydride, how do you prepare the observable? And there are so many studies involving it. If I give you a graph and say find the vertex color, how do you prepare the observable? Again, so many research that goes into this. So this is not something that we will dive into today, but the main goal of these kind of algorithms is this, that you find out what is the property that you want to measure for the system. Once you find out the property, you simply create an observable accordingly. And once you create that observable, prepare the quantum state, measure, you get the expectation value. That's kind of the big template, if you like, that it's a general template for solving this kind of problems. How do we calculate expectation values? So we have seen how to do this here, right? So let's go back and see how it is done using a quantum computer, using a simulator for this case, but it will be exactly similar when we go to a quantum computer. Okay, I think I should zoom in a bit here also. So yeah, I'll share these notebooks with you all. You don't need to worry. I mean, it's already updated in my GitHub. I'll share the GitHub link with you. So this notebook is prepared with the latest version of Qiskit, which is SDK 2.0, and there are some visualization supports required. So if you want to install Qiskit, just say install Qiskit with this visualization. I will use Qiskit Air for simulation, and I will use Qiskit runtime, which is used for actual execution step. So let's come to this particular quantum state. This is a particular quantum circuit. Let us assume that this is coming from some problem, like I said, from some chemistry problem or some graph problem, some machine learning problem. I don't really care from which problem this is coming, because again, that will be like a not just a class, that will be a set of many classes itself. Let's say that someone has done those things and we have a quantum circuit here. Now see what is the property, what are the properties of this quantum circuit? This is just a 2-qubit quantum circuit. It uses an Rx gate, which is a rotation around x-axis, and a C0 gate. This is something that we will call a template circuit. Why so? Because see, the angle of rotation is not defined. I have just created a template that there is some angle of rotation, theta. We will put in the value later. So this is something that I would call a template circuit, that it creates the template, and whenever you want to assign a particular value, you can go ahead and assign it. So these are certain changes that has come to Qiskit recently, that if you want to put in your particular values from the beginning, then say you want to test it for 10 values of theta. So you would create 10 circuits. But if you create a template and just pass in the values, then the parameter assignment is very fast. You save the space of 10 circuits. So, you know, all these things Qiskit keeps updating again and again. So what we will first do, we will first use a backend simulator, which is this AER simulator. I think you have already seen this AER simulator before. So this is my simulator, and I'll use this to run this particular circuit. To run this particular circuit, I want to get the final distribution, the counts right now. So if you want, I want to get this, like what probability with these states are happening. This is all I want to get. I'll calculate expectation value later on, because this is classical. This addition and multiplication is classical. I'll do that by hand later on. So for that, we have two primitives. The first primitive in Qiskit is called sampler, that gives you the distribution, the probability distribution, this distribution. And there is another primitive called estimator, which gives me the expectation value. Now, you should be asking this question immediately, that all you have said at this moment is that what we do on a quantum system, we prepare the quantum circuit that I have already prepared here. We prepare the quantum circuit. we will measure the quantum circuit, we will get this distribution, and then I'll calculate this classically by hand. So why do you need two primitives? If you can get this using sampler, this is just simple multiplication and addition. What is the point of having an estimator primitive? Hold that question. If you have that question, hold on to it. We will answer this question today. For the time being, I am taking this sampler primitive, which will give me the distribution. And I am telling it that, okay, you will run your system on this backend, which is my air simulator. And how many times, this is the number of shots, how many times you try it out? 1000 times. So we have saved this. Now see, when we submit a job to a quantum circuit in Qiskit 1 and version V2, it uses this thing called pub. I remember Janani was telling you about this. So pub is primitive unified block. The K is not missing here. This is not a spelling mistake. It is BLOC. And a pub is a tuple. Simply, it's a tuple. It's a circuit observable parameter. For our case at this moment, there is no observable. I don't want to calculate expectation value. I just want the distribution. So you can either give all three of them, any two of them, like circuit is mandatory. Circuit you need to give, but other than circuit, maybe it's not a parameterized circuit, then you don't have any one of those. If it is a parameterized circuit, for our case, I need to give the parameter. I don't have an observable, so it can be circuit parameter, it can be circuit observable, it can all be all three, it can be only circuit. So it's just a tuple, and you need to pass in whatever your situation is. It will internally understand what you are passing. For our case, I am passing this quantum circuit and the parameter value. So I have chosen pi by 3 as my parameter value theta. This is what I have chosen. Now what we will do, remember that it takes a list of pubs. I have a single circuit at this point. If for your problem you have 10 circuits, you can pass in something like pub1, pub2, pub3, and so on. I have a single circuit, so I am just passing the list of a single element, and I am passing this to sampler to run this. Now this is just a local simulation. This simulation is happening in my laptop. So there is no queue or nothing. But when you will go and run this on a real quantum hardware, many people are trying to use that hardware. So there will definitely be queue. And if you submit it at this point, it may be executed at some later point, maybe an hour later, your circuit gets executed. So will you just like sit in front of the device and just wait when the circuit gets executed? That makes no sense. So very good practice is that keep a note of the job ID. When you keep a note of the job ID, you can just go ahead, turn off your internet, turn off your computer, do other works, and say you come back after 5 hours and you check that your circuit has already run. If you know this job ID, you can retrieve all information from there. You don't need to keep waiting. You don't need to keep having a continuous internet connection. You don't need to keep your laptop open as long as the hardware is on queue. Just keep a track of this job ID and you can retrieve later on. So that's a very good practice. Although, as I said, this is just a simulation that we are doing. There is no queue, nothing. So now we are getting this job.result. And from this result, remember, this is a list. So ideally, I can pass in, say, 10 such pubs, 100 such pubs, and I'll have to retrieve each of this element. I have passed in only one pub, so 0th element of that list. So if we see now, this has a very concatenated structure of data. So if you see, this is what the result looks like. It has a data part, it has a metadata part. Metadata part will contain the number of shots. Yes, this is repeated. And you can give some circuit metadata. Say you want to give some description of what this circuit is about, what problem it is solving. So it will contain all those circuit metadata. And the data part is what we are most interested in at this moment. So let's go into the data part of this. So data part contains the number of shots, the number of bits, which is equal to the number of qubits, and the measurement outcome. Now note this, that this name maze, this is equal to the name given here. So the name by default for the classical register is maze. But if you choose to change the name of this register, say you said that, no, I don't like maze, I will use gamma for this, then this will become gamma. And then you will have to do data.gamma, not data.maze. Okay, so now we have this as the bit array, and from here I can get the counts. So you see, this is my counts. This is 0, 0, 7 roughly 750 times, and 1, 1 roughly 250 times. This is the count that we have got. If you want to know, see, I am trying this out 1000 shots. That means what we just said, you prepare the circuit, you measure it, prepare, measure, do this 1000 times. This is what shots equal to 1000 means. So each time I am getting one outcome. If you want to know for some reason that what are the individual outcomes, you can call this maze.getBitString. So you see there will be 1000 such elements. First time I got 0, 0, 0, 0, 1, 1, then again 0, 0, 2 times. And this is kind of a consolidated thing that, okay, I have seen 0, 0, 750 times. I have seen 1, 1, 250 times. So you can get any information out of this that you want. And for bigger systems, I mean, this is very easy to visualize. It's just a 2-qubit system. But for bigger systems, it can be a very cumbersome dictionary. So what you can do is you can just plot the histogram, and it gives you an immediate pictorial view of how the counts are varying. So this is 752, this is 248. Now, as we said that we want to calculate the expectation value, and how do we calculate the expectation value? I have the probability distribution. I have this distribution here, how many times each of the elements has occurred. See, I know that 750 times 0, 0 has occurred, 248 times 1, 1 has occurred. So what I'll do is I'll simply do this calculation by hand. So let's do that. So I have selected my observable to be ZZ for this case. I have selected my observable to be ZZ, which kind of means that I am measuring the spin along Z direction for both the qubits. So I prepare my observable. The observable is prepared by calling this parse-Pauli op from qiskit.quantuminfo, and I am just passing it that this is what I want to measure. Now I could have just done that calculation manually also, like this multiplication, addition manually also. But there is also a function in qiskit.result called sampled expectation value. If you pass in the counts, so remember counts is this is my counts. So if you pass in the counts and the observable, it is actually doing that calculation only, that multiplication and addition. So let's do that. So we see that the expectation value is 1. Let's try out another expectation value here. Let's take Zi. So Z on the first qubit, I on the second qubit. We see this is 0.5. Now, if you do this calculation by hand, maybe this will be slightly different, because we are taking these samples, and we know that if we could ideally take infinite samples, we will get the exact expectation value. But since we are taking some finite number of samples, if you mathematically do the calculation by doing this shy kind of calculation, this can vary slightly, not significantly. Maybe on the second or third decimal place, this can vary a bit. Now let's come to a second question. Let's say that I want to measure the expectation value of XX. What does it mean actually to measure the expectation value of XX? Sorry, what happened here? Yeah. So what does it mean to measure the expectation value of XX? Simply, if we want to write it down in terms of, okay, let's come here. How do we mathematically calculate. If I give you psi, then, and if my observable is O, this is how we mathematically calculate expectation value. So for our case, O was ZZ till now. Now, if I say that you want to calculate XX, then it will simply be psi, XX, psi. What this means physically is that we need to measure this in X basis. So what this meant physically is measure this means psi, measure psi in Z basis. Now Z basis is the computational basis. So all type of measurements that we do on a quantum computer is Z basis measurement. All measurements in QC is in Z basis. Now the point is, a quantum computer, this is not only for IBM quantum computer, no quantum computers today can measure in any other basis. So how do we do this? How do we do this? Because this needs that you measure your system in X basis. If you have something like, say, psi yi psi, just to make this means measure psi in Y basis. Even if it is yi, what you can do is measure the first qubit in Y basis, second qubit in Z basis. If it is I, you can still measure it in Z basis. But for the first qubit, you need to measure it in Y basis. But again, like I said, that we do not measure in anything other than Z basis. And you will see there are so many protocols, like I'm not sure if you have already done that. If not, there are many protocols like teleportation, dense coding, which says that you need to measure in something called Bell basis. But we do not measure that. So what do we do? See, when we are measuring something in a basis, it is like observing it along the Z direction. When I say measure in Z basis, it simply means observe along the Z direction. Now, when I say that measure in X basis, then it means observe along the X direction. But if I say that, I cannot observe along the X direction. So let's take an example. You will see sometimes we get this type of pictures, right? That when you see this in this way, it looks something. If you rotate the picture, it will look something different, maybe. So since I am holding my phone like this, I can see this way of the picture. I cannot rotate my head. Ideally, if I want to see it upside down, I should be rotating my head, say 90 degrees or 180 degrees. Since that is not possible, what do we do? What do we do? We just rotate the phone, right? We would take and rotate the phone. And this is the same idea that we will do here. It says that you need to measure in Z basis. That means observe in Z direction. Now this means observe in X direction. But my quantum computer doesn't know how to observe in X direction. So let's rotate the quantum state itself such that I can now observe it from the Z direction. How to do that? How to do that? So this is an identity. This is an identity that X is equal to Hadamard, Z gate Hadamard. So now let's take this as a single qubit, right? Just for simplicity, just for simplicity. So what I can say is this is actually HZH psi. I can write this. Now just look into this. What this means. What is this saying? It is saying that you have a quantum state psi, apply Hadamard gate on it. If you apply Hadamard gate, your basis changes from X to Z. So if I write something like H acting on psi is equal to, say, call it psi H, then this is exactly equal to saying this. And I know how to do this because I need to observe the system in Z basis and my quantum computer can do that. So this is as simple as saying that if you want to measure in a different basis, you need to apply the appropriate rotation gate. When you want to measure in Y basis, rotation with Hadamard will not work. It will require an edge dagger gate followed by a Hadamard gate. So whatever basis you are thinking of, say you come up by saying that, okay, I have thought of a different basis, some theta basis, then somehow I need to come up, I need to know what is that rotation required, and I need to apply the gates accordingly, right? But okay, but for X basis measurement, this works. So all it says is you need to apply a Hadamard gate on your actual circuit and then just measure in Z basis. That's it. So here, see what we do is I have created a copy of the quantum circuit. I need to remove my final measurement because I am going to measure in XX. So I need to apply Hadamard gates. So when I say remove final measurements, it just removes these measurements because I now need to apply a Hadamard here. So I have removed these measurements. I have applied Hadamard gate here, and then I am just measuring it. So it's this circuit. And again, I am going to run this pub. It's the same pub, just that the circuit is now QCX, measurement in X basis. I'm just doing this sampler.run, sending it a list of pubs, getting the result, 0th element, go to data, go to maze, remember maze, get counts. And you see, this is a different result. This is a totally different result. Previously, remember, it was an entangled state. It is no longer entangled in the X direction. Great. So now we can just go and say sampled expectation value. I will pass in this but outcome, and remember, once I have created this quantum state, the expectation value calculation is now on Z, no longer on X, because I have done the proper rotation. So once I have done this rotation using Hadamard gate, once I have done this, now measuring XX is equivalent to saying that I am going to measure ZZ on this modified circuit, right? So I'm just going to pass my observable ZZ, which was, if you remember, which was this sparse Pauli of ZZ, to my new counts X, and that will give me the expectation value, which you see is roughly 0.022. Nice. So similarly, for Y observable, we can do the same thing. Now let's come to that question that we were asking. I have done all of this expectation value calculation without using estimator. And I have said in the beginning that there are two types of primitives: sampler to get the probability distribution, estimator to get the expectation value. And I myself asked this question that if you can do this as simple as this, why do we even need an estimator? So here is a point. Let's say I have a 2-qubit system and I have two observables to measure, ZZ and ZI. These two observables commute with each other. So I know you all know, but just for the sake of completeness, commutation means that if A and B are two matrices, then AB is equal to BA. The order in which these matrices are applied is irrelevant. This is not true for most of the cases. But ZZ and ZI, these commute with each other. And when they commute with each other, what I can do is I can use the same distribution to calculate the values of, calculate the expectation value of both ZZ and ZI. And if you see, this is what exactly I have done. I have measured this only once previously. I measured this only once. I took this outcome and I used it to calculate the expectation value of ZZ. I used it to calculate the expectation value of ZI. I could have used it to calculate the expectation value of IZ as well. But not all matrices commute. So if I have something like ZZ and XI, they don't commute with each other. So what it means is if you first, so this doesn't require any Hadamard gate. This requires Hadamard gate. So whether you want to calculate this first, this next, or this first, this next, that will create a problem in your outcome. Your outcome will not be the same because A times B here is not equal to B times A. So in this case, where the observables don't commute with each other, I need two circuits. One circuit will calculate for this, one circuit will calculate for this. Hopefully this is fine. So I need two circuits. Let's take another example. I have Zi and Ix. So remember, if you in case you don't remember, Z and X anti-commute. Z and X is not equal to X and Z. Rather, it's basically Zx is equal to minus Xz. So they anti-commute. What happens when we have a two observables like this? See, let's put them one after another. Let's put them one after another. This was my observable. Z and I commute with each other. I is identity, it commutes with everything. X and I commute with each other. Z and X anti-commutes, but they are on different qubits. So the anti-commutation doesn't come here. So what I can do is, if I have a 2-qubit system, I don't need to do anything for this first qubit. I'll put a Hadamard on this second qubit. I am done. One circuit can calculate the expectation value of both of them. So now here comes the question that this was a very easy example. If I give you say 100 qubit with say thousands of observables, will you like keep on doing this manually again and again, trying to find, see, one thing that you could do, say I have thousands of observables, I'll just use a different circuit for each, say I have a 1000 terms in my observable, I'll use one circuit for each of the 1000 terms. That is something you can do. If you do that, you can just use this method. You prepare the circuit, get the distribution, calculate this manually, just as what we have done. But that is highly inefficient because maybe even those 1000 terms, maybe you could have just done with 100 circuits. Why do you want to run 1000 circuits for that? That's highly inefficient. But then comes the question that this is not very easy. Like this was a very simple example. But when I have like a huge system, huge number of observables, how do I find out efficiently that which of the observables commute? I'll group them together and I'll use a single circuit for that. So I need to find groups from that terms of observable such that I can use only one circuit for that entire group. That this is how we make things efficient. Let's take this example here. So you see, I have taken 4 observables here. And unless you have been working with these kind of things for many days, it is not trivial to just look at all 4 of them and say which one commutes, which one anti-commutes, which can be grouped together. See, when I say you can group things together, that means that you can kind of use a single circuit for that. Zi, Zx, and Ix, they can be grouped together. They don't anti-commute with each other because this is Z on the first qubit and I on the first qubit. No anti-commutation. Then X on the second qubit or I on the second qubit. No anti-commutation. So although I have 4 terms here, I need one circuit for all 3 of them and I need a second circuit for Yx. Now this type of calculation, how many circuits are needed? What are the commuting groups? What is the minimum number of circuits that you can use? This is something that is done in the underlying calculation by estimator. Estimator is not just a fancy thing that we have that we could have like done away with, that perhaps we don't need estimator. It's not like that. This is the main purpose of estimator, to do this underlying calculation, find the minimum number of circuits that we require to calculate the observables. prepare the circuit, not just finding the minimum circuits, apply which rotations are required on which qubit accordingly. This is the main underlying work of estimator. So let's do this with estimator. For that, again, just like sampler, we import estimator v2 from Qiskit IBM runtime, and I just pass in mode equal to backend. For estimator, we don't give the final measurement. We don't give these measurements. Why not? Because estimator will decide how many circuits are required and which rotation is required on which circuit. So I just pass in this circuit. Estimator will prepare copies of it, just like I prepared copy here manually. I prepared a copy. I applied Hadamard gate. These things estimator will take care of. So estimator decides how many copies of these are required, what are the rotations required on each qubit, and then finally puts in the measurement. That's why measurement is not allowed when we put estimator. It is using measurement eventually, but after putting in the proper rotation. So let's say that I have used this observables. So these are my observables here. These are individual observables. Zi, Zx, Yx, Ix, Zz. Now I put in my pub. Remember, my pub was circuit observable parameter. In this case, I need all three. I need my circuit, I need my observables, which is this, and my parameter, which is 503. So I'll again put in job equal to estimator.run. Just one small thing to point out, because this will come very handy later on. This is a list of observables. What I am saying to estimator is, I want to know the expectation value of each one of them. So estimator will return me a list of values, each corresponding to each observable. So let's just run. So I'll do this job equal to estimator.run. I send in the pub. My result again is job.result. When it comes to expectation values, it is result.data. Previously, there was a mess where we were, where we were going into the classical register. That doesn't happen here. We don't want the counts. We want the expectation values. EVS stands for expectation values. So you see, these are my expectation values. I passed in 1, 2, 3, 4, 5 observables. I have got 1, 2, 3, 4, 5 expectation values. Awesome. Now say you are saying that, no, I want to calculate something like this. You can do it manually. You have the results for each one of them individually. Just manually multiply and add or subtract. Here, we got it. There is one more thing that we can do using estimator. Let's say you want the expectation value of this observable only. You don't care what the individual values are. You care about what this entire observable O, the expectation value of this entire observable O. I don't care about each and individual term. So I don't need the values, these individual values, and I don't want to manually do this calculation. If that is the case, then what you can do is you can say that, okay, this is the sparse-Pauli op. This is the list of observables, and these are the corresponding coefficients. See, the coefficients are 0.1, minus 0.5, 0.3, 0.2, minus 0.4. So this is my observable. This is what my observable looks like. And if you want to know, so see, out of this 5, the grouping that I was talking about, that's kind of the main work of estimator. It has already grouped that this is one group. These 3 commute with each other. This is the second group. They commute with each other. So although I have 5 different observables, I only need 2 circuits for execution. And now if I just pass in this pub, which is QC, this new observable obs, which is this linear combination, and pi by 3 has been my parameter. So just do estimator.run, and let's look into the combined expectation value. You see, it's roughly same, minus 0.612 minus 0.618. Sure, as I said in the very beginning, that in the third decimal place or second decimal place, there can be some variations, because ideally you need to take infinitely many shots to get the exact expectation value. Like for example, we say that when we toss a coin, it's 50-50 head and tail. But if you want to see exact 50-50, you have to take infinitely many values. If you don't take infinitely, if you try 10 times, maybe you will get 6 and 4. It's not 50-50. So that kind of thing remains here. I hope this was clear and this was useful. So we'll just do one small thing, before going into the break. So let's look into what happens when we run this on a real backend, but instead of taking a real backend, because there is a wait, audio lost. Am I still audible? Okay, okay. Yeah, so as I said, that there can be a lot of queue, and the same thing will happen to me also. We don't get any extra privilege. Okay, so the same thing will happen to me also. If I want to go and run on a real hardware, it will become very awkward that I'll pass on to the hardware and let's sit silently as long as your queue, as long as I am in the queue. Okay, yeah, we can take these questions. Wait, let me stop sharing and look into the questions. Yeah, interpreting the value of observable physically, it is very difficult for this problem, because I have not taken this problem from some physical systems. I have just said that, this is just a quantum circuit and this is an observable. But if you would have taken this from some problem of interest, say chemistry, maybe then you could have said that minus 0.6 is the ground state energy. If it were from a graph theory problem, maybe you could have said minus 0.6 is proportional to, not equal to, some, say, graph property or something. For this particular case that I showed, minus 0.6 is just a mathematical value. It does not have a physical interpretation. If we do many number of shots to get the correct value, isn't it similar to overfitting? So yeah, there is definitely a statistical calculation that you can do, that what is the number of shots you need. It is not exactly overfitting. The reason is, see, quantum computers are random. We know that it's probabilistic. Even when we do randomized algorithm classically, we need to take many iterations. We need to run it again and again. So you see, the way we give the complexity of any classical randomized algorithm is the expected number of shots you need to solve this. So that you get by running it again and again. So this is randomized. We do need to get this kind of many number of shots, but there is a mathematical calculation that you can do, that if you want if you want it within some particular error, say epsilon, what is the number of shots that you need? If you go beyond that, definitely it's overfitting, and definitely it's like using more resource than you need. Okay, yeah, thanks for the questions. So yeah, this is my fake backend. This is a very favorite backend of mine, just because I am sitting in Kolkata. So naturally, it's a very favorite backend for me. This is what the backend looks like. You have already seen this before. So this is called the coupling map, and we have all this noise information. So you see all this readout noise information here, and gate errors. These will give you single qubit gate errors. This is a very noisy 2-qubit connection. So all this noise information, these are also available. So you can even get the values from here. When we need to run it on a real backend or fake backend, as you know, it basically mimics the real backend. So we need to transpile this circuit. To transpile, I know you have already seen this. So we do this generate preset pass manager. I am passing in the optimization level and backend equal to fake backend. Now, if you remember from one of the last lectures, there are 6 stages in a pass manager, and you can actually see the stages by just calling pm.stages. These are the 6 stages. This is a very small circuit. So, this is a very small circuit. There is not a lot of optimizations that can happen for this circuit. So two things are very important. First is, we know about basis gate set, right? Rx is not a basis gate set. So I need to break down my circuit into the set of basis gate sets. So these are the gates that the quantum computer understands. Just like classically, we know that if I give you and or not, you can build any logic function. So basis gate sets are exactly like that. If I give you those unitaries, you can build any unitary by concatenating them. So one of the first stage, I'll just show two stages here. So as you know that, as I just said, that all these optimizations and all this is such a small circuit, it doesn't really work here. I mean, it doesn't really need to work here. It will work here. First stage you will see is translation. The first actual stage that is going to work a lot is translation. So you see, it has broken down Rx gate into this many gates. If you want to see what are the basis gate sets of uh, this particular backend, you can just go to backend.configuration.basis gates. So it is identity RZ SX, this is square root of X, X C naught bisect. So you see, it has broken it down into these. The other question that needs to be answered is these virtual qubits. Look into this. These virtual qubits, Q0, Q1, which are the physical qubits that I want to put them on? And this actually has more than one main thing to consider. First is that that long distance C0s are not possible. So if I put, say, Q0 here and Q1 here, I'll have to do swap gates. I need to minimize the swap gates. Second thing, simple. Think of this. If I say, do you want to use 1, 2 or 11, 14? You will all say 1, 2 because 11, 14 is more noisy. So looking into the circuit, first find me one placement that is going to reduce the number of swap gates. Second, find me that placement that will also reduce the noise. I don't want to use 11, 14. So this is the second thing that layout does. And if you see layout, it has selected qubit 8 for Q0 and qubit 9 for Q1. And when you actually do the entire pass manager, you will get a combination of both of this. Let's run. So you see 8, 9 layout is preserved and this translation is also preserved. So it's kind of doing both of the thing at the same time. Of course, if this were a way more complicated circuit, there would have been a lot more optimization and other things. The other four things are here also very important. They are not just there, but this is a small circuit. So let's again run this on a fake backend. It's simple. I'm going to run this on sampler. So I have this ISA QC. This is my parameter. I have used mode equal to fake backend. So it is going to run on fake Kolkata. And now my noisy counts is this. So just remember, let's come back to this for a second. My original count, this is my original count. It should have been only 0, 0 and 1, 1. This was an entangled state. But because there is noise, you see I am also getting some 0, 1 and 1, 0. Entanglement is lost. So let's look into this. This is what noise does. But let's look into the expectation value calculation. This was the, so again, I am going to remove my final measurement because estimator will take care of which rotations to put, how many circuits we need and everything. So this was the actual observable that we measured here, and we got the value to be minus 0.61, something like this. Let's do the same thing, but just one, this is very important. This is actually very important. See, these are defined over 2 qubits, Zi, 2 qubits. I have placed my Q0 on qubit 8 and Q1 on physical qubit 9. So if I now say that, oh, okay, I'll measure Zi on physical qubits 1 and 2, this is incorrect. I need to make sure that when I have changed my Q0 to 8 and Q1 to 9, my observable should also reflect that. Otherwise, my measurement is incorrect, right? So we don't have to really manually take care of that. There is this very nice function called apply layout. It just takes the layout from this transpiled circuit and it creates an ISA observable. See, there is no instruction set architecture in observable. It's just like a similar nomenclature. So now you see, Qiskit reads from right to left, right? So 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. See, we wanted 8 and 9. So these are all now properly managed on qubits 8 and 9, putting identity on all other qubits. So let's go to estimator and run the expectation value. You see, I get minus 0.57. My actual value was minus 0.62. So we'll just stop with this last one thing. And this is where we will come back to after this break, is when you look into this circuit, you will say, when you look into this result, you will say it should have been 0, 0 and 1, 1. It should have been an entangled state. You are getting 0, 1 and or 1, 0 also. You are way off. It should have been entangled. It is not even entangled now. There should have been no 0, 1 or 1, 0. So this is like a complete mess. You can come and say that. Someone who is a bit optimistic can come and say that, okay, I understand the results are a bit off, but 0, 1 and 1, 0, they are very low. Can we think of something? So there can be a problem here. Those who are very very not at all flexible, very concrete, they will say no, it should have been 0, 0 and 1, 1. I cannot have any 0 and 1 and 1, 0. But those who are a bit optimistic will say, okay, this is wrong, this is slightly wrong. How can I capture this thing? It is wrong, but it is slightly wrong. It is not too much wrong. That is something that also gets captured into expectation value. When you look into this kind of counts, you will say this is a disaster. There should have been no 0, 1 and 1, 0. But if you look into the expectation value, you would say it should have been minus 0.61. You are at minus 0.57. Okay, you are off, but you are not too way off. So what I just discussed here, that trying to capture this essence that there is noise, but not too much noise. This kind of information also gets better captured in expectation values. So we will stop here for the break. And what we will come back to is, we will see that when we get this noisy expectation value, at least for the measurement error types, we can actually mitigate the effect of noise and actually get the effect of what would happen if there were no noise. So let's stop here for this. Yeah, so we can take a break now. So let's stop here. And if there are any questions immediately, we can take, or